When we hear about black holes, it's common to picture giant cosmic monsters that suck in everything around them, like space vacuum cleaners. Once something crosses the edge of a black hole, there's no turning back, and that includes light, the fastest thing in the universe. That's why, theoretically, black holes don't emit light, unlike stars, which produce photons in their core and release them into space. So how can we explain the fact that yes, black holes can shine? It sounds contradictory, I know. After all, if not even light can escape a black hole, how could it possibly glow in any way? The answer lies in a phenomenon discovered by Stephen Hawking in the 1970s called Hawking radiation. And despite its technical name, this discovery brought profound implications for modern physics, and even for the ultimate fate of the universe. But before we understand how this all works, we need to dismantle a bit of the image we have of black holes. Unlike stars, planets, or even neutron stars, which are made of matter in different states, solid, liquid, gas, or plasma, a black hole isn't made of matter in the traditional sense. It's a region of space-time with such intense curvature that nothing can escape its gravity. If you were to fall into a black hole for some reason, you wouldn't see a dividing line. You'd continue seeing the sky as usual until, at least in theory, your body would be crushed by the singularity at the center. But the key idea here is that a black hole is defined by a boundary called the event horizon. This is the point beyond which gravity becomes so strong that nothing, not even light, can escape. To an outside observer, it looks like a completely dark sphere, but it's not a solid ball, it's a region in space. This more accurate view of black holes is essential to understand Stephen Hawking's work. He was one of the few people who managed to find a real connection between general relativity, which explains how gravity works on large scales, and quantum mechanics, which describes how tiny particles behave. These two theories were developed in the 20th century, but even today they don't fully match up. Einstein developed the theory of general relativity to explain the macrocosm, planets, galaxies, and the curvature of space. Meanwhile, quantum mechanics was created by physicists and chemists to understand the microcosm, atoms, electrons, and subatomic particles. Curiously, Einstein is famous for relativity, but he won the Nobel Prize for a discovery related to quantum mechanics. Despite that, he disliked this branch of physics because it's based on probabilities, not absolute certainties, which led to his famous quote, "God does not play dice with the universe." Even with that tension, both theories work extremely well within their own domains. The problem comes when we need to apply both at the same time, as happens with singularities. For example, at the center of black holes or at the Big Bang. Einstein spent the final years of his life trying to unify these two areas, but never succeeded. It was in this context that Hawking began to stand out. He started by studying relativity and black holes, and even proposed a rule stating that black holes never decrease in size. But later, he began studying the effects of quantum mechanics in the regions near the event horizon. That's when he noticed something strange. His calculations showed that black holes could, in fact, lose mass over time. Not only could they shrink, they could also slowly evaporate. This revolutionary conclusion came with an even more shocking observation. Black holes could emit radiation. In other words, they could, in a way, shine, even if that shine is extremely faint and difficult to detect. This radiation, named Hawking radiation, sparked a lot of controversy at first, but over time it became one of the most respected ideas in theoretical physics. But how does this actually work? Well, it all starts with the idea that the vacuum of space isn't exactly nothing. According to quantum mechanics, space is filled with quantum fields, as if each type of particle had its own invisible field spread throughout the universe. And in these fields, because of something called the Heisenberg uncertainty principle, there are always random energy fluctuations, even in a vacuum. These fluctuations allow pairs of particles to pop in and out of existence all the time. These are known as virtual particles. They exist for an extremely short time, just long enough not to violate the laws of physics. And believe it or not, this phenomenon has already been confirmed by experiments like the famous Casimir effect. These virtual particles are constantly forming and annihilating themselves throughout space, including the region around a black hole's event horizon. Normally, these particles appear in pairs and vanish right away, canceling each other out. But sometimes the black hole interferes with this balance. When such a pair forms right at the edge of the event horizon, one particle might fall into the black hole while the other escapes into space. The one that falls in is lost forever, but the one that escapes carries away a tiny bit of energy, and that energy doesn't come from nowhere. It's pulled directly from the black hole. For every particle that escapes, the black hole loses a bit of mass. And since mass and energy are equivalent, this process gradually reduces the size of the black hole. This is the real mechanism behind Hawking radiation, a purely quantum effect that turns black holes into extremely faint emitters of radiation. From the outside, what we see is a particle of light, a photon, escaping from the black hole. Since these photons have a specific frequency, it looks like a faint glow. Of course, it's not a visible glow like that of a star, but it's still radiation. Hawking went further and was able to relate the temperature of this radiation to the mass of the black hole, using an equation based on the Schwarzschild radius, which is the radius of the event horizon. This temperature determines the spectrum of the radiation emitted. In other words, the smaller the black hole, the higher its temperature, and the more intense the radiation it emits. Large black holes, like the supermassive ones at the centers of galaxies, emit very little Hawking radiation, so little that it makes practically no difference in their mass. But tiny black holes, if they exist, could emit radiation intensely and evaporate quickly. This brings us to a fascinating idea. Black holes can die. By emitting radiation, they lose mass, and over time they become smaller and hotter, emitting even more radiation in a cycle that speeds up until they vanish completely. But don't worry, this won't happen to the gigantic black holes we know anytime soon. Most of them are still feeding on gas, dust, stars, and even entire planets. Even if they lose a minuscule amount of mass through Hawking radiation, they continue to grow because of all the matter they absorb. In other words, black holes today are, in practice, very much alive. Hawking radiation is already happening, but the process is so slow that it doesn't significantly affect these cosmic giants. Now, if we're talking about very small black holes, like the hypothetical primordial black holes that may have formed shortly after the Big Bang, then the story could be different. For those, Hawking radiation could be so intense that they'd evaporate quickly, in fractions of a second. We still don't know if these primordial black holes really exist, but if they do, there's a chance we could detect them. That's because, in the final moments before completely disappearing, they would release a burst of extremely energetic radiation, mainly gamma rays. Detecting one of these explosions would be like witnessing the last breath of a black hole. Even more fascinating is thinking about the future of the universe. One day, all the stars will go out, galaxies will stop forming new stars, and the universe will become a cold and dark place. In that distant scenario, black holes will be the last major objects still in existence. They will continue to emit Hawking radiation, slowly losing mass, until eventually they too cease to exist. This stage is known as the black hole era in cosmic chronology, and it could last for an incredibly long time. To give you an idea, some calculations suggest that the largest black holes could take up to 10 to the power of 60 or even 10 to the power of 100 years to evaporate completely. That's a 10, followed by 100 zeros, a number so absurdly huge that the current 13.8 billion years of the universe looks like a blink in comparison. It's almost poetic to think that something so tiny and undetectable today, Hawking radiation, might one day be responsible for the end of black holes and perhaps the final physical event in the universe before everything fades into a silent, eternal void. But despite all this theoretical impact, it's important to remember that Hawking radiation hasn't been observed directly yet. And the reason is simple. It's just too weak. Imagine trying to measure the glow of a candle next to the sun. That's basically what happens when we try to detect this radiation near a black hole. The accretion disk, that ring of matter spinning around the black hole, shines so intensely that it completely outshines any trace of Hawking radiation. Even so, science has found clever ways to study similar phenomena. Laboratory experiments have managed to simulate analogous effects using systems like Bose-Einstein condensates, a special state of matter at temperatures close to absolute zero. A study published in Nature in 2019 showed that under certain conditions, it's possible to replicate the behavior of virtual particles, just like what happens around the event horizon. These experiments don't directly prove Hawking radiation, but they do show that the theory works and aligns with what we already know in physics. Another example is the Casimir effect itself, which confirms the existence of quantum vacuum fluctuations. All of this strengthens the idea that Hawking radiation isn't just a beautiful theory on paper, but a natural consequence of the laws that govern the universe. It aligns with everything modern physics has already validated. Nothing contradicts it. And even without direct observations, scientists haven't given up. There are ongoing projects trying to identify signs of Hawking radiation coming from primordial black holes. One of them is the HESS telescope system. which scans the sky for gamma-ray bursts that could be the result of very small black holes evaporating. If we ever manage to capture one of these explosions, it would be the first direct evidence of this phenomenon's existence. If that happens, it would be a giant leap, not just for proving Hawking radiation, but for bringing together two of the greatest theories in physics, general relativity and quantum mechanics. Unifying these fields is one of the greatest goals of modern science, and Hawking radiation might be one of the keys. After all, it's one of the few ideas that applies quantum concepts to regions where gravity is extreme, like near a black hole. With his brilliant mind, Hawking was able to see that connection where no one else could. He showed that black holes aren't just cosmic devourers, but also subtle emitters of energy. And more than that, he showed that even the most powerful giants in the universe are subject to time, that nothing is eternal, not even a black hole. Today, with the advancement of technology, we have real chances of confirming what was once just theory. We've already managed to capture the first photo of a black hole. And who knows, maybe soon we'll also be able to detect its faint radiation. If that happens, we might be closer to answering a question Einstein himself pursued for decades: the unification of physics into a single theory that explains everything. And that, perhaps, is the greatest lesson Hawking radiation leaves us. No matter how invisible, untouchable, or eternal something may seem, there's always a way to question it, investigate it, and uncover the truth. That's how science moves forward, step by step, with humility and curiosity. And who knows? Among so many unanswered questions, maybe this will be the generation that finally sees the universe reveal its deepest secrets. If you found this topic as fascinating as I did, don't forget to like this video and subscribe to the channel. That really helps this content reach more people who also love science and want to understand the mysteries of the universe. Leave a comment down below. What do you think? Will we one day manage to unite relativity and quantum mechanics? Or are we facing a puzzle that not even time will solve? I'd love to read your opinion. Thanks for watching, and see you on the next journey through the cosmos.